Have you ever looked up at the night sky, at that vast star-dusted canvas, and wondered if it's all just a program? What if our lives, our thoughts, our deepest feelings are nothing more than lines of code running on some unimaginably powerful cosmic computer? This isn't just a question for late-night science fiction movies anymore. It's a serious idea, known as the simulation hypothesis, that has captured the minds of philosophers and physicists alike. The central thought is simple, yet profound. Our entire universe, from the smallest atom to the largest galaxy cluster, might be an artificial reality created by a more advanced civilization. It's a concept that challenges the very foundation of what we call real. The idea has been around for a while, echoing in ancient philosophy. But it was philosopher Nick Bostrom who truly brought it into the 21st century. Back in 2003, he laid out a compelling argument. He suggested that if any civilization ever reaches a point where it can create ancestor simulations, highly detailed simulations of its past, it would likely create countless of them. If that's the case, the odds are that we are far more likely to be living inside one of these many simulations than in the one original base reality. Tech visionaries like Elon Musk have since brought this mind-bending idea into the mainstream, famously stating the chances we are not in a simulation are 1 in billions. So why is this conversation exploding in 2025? It's because the line between our world and a digital one is getting blurrier every single day. We are building our own virtual worlds, creating artificial intelligences that can learn and reason, and pushing the boundaries of computing. As our own technology begins to mirror the power we once only imagined, the idea that someone or something else has already done it on a cosmic scale becomes less of a fantasy. We are, in a way, following a potential roadmap that might have been laid out by our own creators. The question is no longer just philosophical, it's becoming a tangible, scientific inquiry. This journey forces us to put on our cosmic thinking caps. It asks us to be humble and to consider that our perceived reality might be a carefully constructed illusion. Think about it. Every law of physics we discover, every mathematical constant we measure, could simply be the rules of the simulation. They might be the programming that governs how our universe operates. As we peer deeper into the cosmos and the building blocks of matter, we are not just exploring nature. We might be reverse engineering the most sophisticated piece of software ever written, trying to understand the intent of the programmer who set it all in motion.
If our universe is a program, then the laws of physics are its code. And just like any code, it might have certain telltale signs of its artificial nature.
One of the most electrifying new clues comes from the work of physicist Melvin Vopson. His research, Making Waves in 2025, proposes a fascinating link between information and the universe itself.
I've suggested that information is not just something we use to describe reality, but that it might be a fundamental state of matter, just like solids, liquids, and gases. I even speculate that information has mass, a concept that could revolutionize our understanding of the cosmos and its unseen components like dark matter.
This idea leads to a mind-blowing prediction. Vopson's theory, sometimes called the mass-energy information equivalence principle, suggests that as a system's information content grows, so does its stability. Applied to the whole universe, this implies a kind of cosmic data compression at work. The universe, according to this view, naturally trends towards simplifying its information structure, much like a computer file being zipped to save space.
I believe this tendency could be a detectable law of physics, a second law of infodynamics. Finding evidence for such a law would be a monumental discovery, strongly suggesting our reality is optimized for data storage, just like a simulation.
But the most stunning part of Vopson's work relates to gravity. He has boldly predicted that we might be able to detect the information content of the universe by studying gravity itself.
If elementary particles do indeed store information about themselves, this information should have a tiny but measurable gravitational signature. My recent proposals outline experiments designed to detect these subtle gravitational anomalies.
Just imagine if we could prove that information has a physical gravitational effect. It would be a powerful piece of evidence. It would suggest that reality is, at its core, made of bits of information, governed by processing rules we call physics.
Think of it this way. When you play a video game, the game world seems solid, but it's all just information. The game's physics engine only calculates what it needs to, when it needs to. It simplifies and takes shortcuts to save processing power. My work hints that our universe might be doing the same thing. The laws of nature, including gravity, might be elegant algorithms designed for efficiency.
If his experiments in the coming years succeed, we would have to face the stunning possibility that we are living inside a grand cosmic computer, where even the force that holds the stars in their orbits is part of the program. Let's dive deeper into the strange and wonderful world of the very small. This is the realm of quantum mechanics, where particles can be in multiple places at once and can be linked across vast distances in an instant. It's a world that seems to defy common sense, and to some, it looks suspiciously like the inner workings of a computer simulation. In a simulated world, reality wouldn't need to be rendered until someone is there to observe it. Sound familiar? In quantum physics, the properties of a particle, like its position or spin, are often not definite until we measure them. It's as if the universe waits for an observer before it decides what to show.
The advancements in quantum computing in 2025 are adding another layer to this mystery. We are now building machines that harness these bizarre quantum properties to perform calculations that would be impossible for even the most powerful classical supercomputers. These quantum computers don't use simple on or off bits like your laptop. They use qubits that can be both 0 and 1 at the same time. This allows them to explore a vast number of possibilities simultaneously. As we get better at building these machines, we are learning what it takes to simulate complex quantum systems, and we're finding out it's incredibly difficult.
This difficulty itself is a clue. The sheer computational power required to simulate even a small corner of the universe is astronomical. Physicists have calculated that to perfectly simulate a few hundred atoms, you would need a classical computer larger than the known universe.
This might seem like an argument against the simulation hypothesis, but what if the simulators aren't using classical computers? What if they are using quantum computers? The very nature of our quantum reality might be a sign that it's running on a quantum hard drive. Our universe's weirdness at the quantum level could be a direct reflection of the hardware it runs on.
So, when we build our own quantum computers, we might be doing more than just creating a new kind of technology. We could be building a machine that operates on the same principles as reality itself. Every successful quantum computation, every milestone we reach in controlling the quantum world, brings us one step closer to understanding the potential architecture of a simulated cosmos. We are learning the language of the universe's operating system.
The question then becomes, if we can eventually build a quantum computer powerful enough to simulate a universe of its own, are we just continuing a cycle started by our own creators?
Of course, not everyone in the scientific community is ready to plug into the matrix. For every proponent of the simulation hypothesis, there's a brilliant mind urging caution and skepticism. Science, after all, thrives on doubt and rigorous testing, not just fascinating ideas.
One of the most prominent skeptical voices is, well, me, Sabine Hossenfelder. I argue that the simulation hypothesis, while intriguing, is fundamentally unscientific. My main point is that for a theory to be scientific, it must be falsifiable. That is, there must be some conceivable experiment that could prove it wrong. How could we ever definitively prove we are not in a simulation? Any evidence we find could simply be part of the simulation's design. If we discovered the universe was made of pixels, the simulators could just make the pixels smaller. If we found a glitch in the physics, it could be explained away as a feature, not a bug. The theory can twist and turn to accommodate any new data, making it impossible to pin down. So I suggest that instead of spending time on what I consider a philosophical game, scientists should focus on testable theories that can be confirmed or denied by experiment. It's a call to keep our feet planted firmly in the observable, verifiable world.
Another Nobel laureate, Frank Wilczek, offers a different kind of critique. He looks at the universe and sees not computational efficiency, but messiness and needless complexity. A programmer, he argues, would likely build a universe based on simple, elegant rules. But our universe is full of arbitrary constants, strange particle masses, and forces that seem cobbled together rather than elegantly designed. He points to the ugliness of the standard model of particle physics, with its many unexplained parameters. Why would a simulator create such a complicated and seemingly inefficient system? To Wilczek, the universe looks less like a clean piece of code, and more like, well, nature.
These skeptical arguments are crucial. They serve as a vital reality check, reminding us that an idea being popular or cool doesn't make it true. The burden of proof lies with those who support the simulation hypothesis. They must provide concrete, testable predictions that can't be explained away. Without that, the theory remains in the realm of metaphysics, a fascinating what-if scenario that fuels our imagination, but doesn't advance our scientific understanding. The debate between believers and skeptics pushes science forward, forcing both sides to sharpen their arguments and search for better evidence to support their claims.
Let's say for a moment that we find definitive proof, an undeniable signal, a law of physics that screams simulation. What would that mean for us, for humanity? The philosophical implications are honestly staggering. Our entire understanding of reality would be turned on its head. The search for ultimate meaning, for a divine purpose, would suddenly become a search for the purpose of the simulation. Were we created for an experiment, for entertainment, or are we simply a byproduct of a simulation designed for something else entirely? These questions would dominate human thought for generations to come. Then there's the question of free will. Are your choices truly your own, or are they predetermined by the simulation's algorithm? If our consciousness is part of the code, is our sense of freedom just an illusion, a programmed response to stimuli? It's possible that even in a simulation, there could be room for genuine choice, perhaps as an emergent property of the system's complexity. But the doubt would always linger. Every decision, every creative act, every rebellion would be shadowed by the question, was I programmed to do that? It's a thought that could be either paralyzing or strangely liberating. This new cosmic perspective could also reshape our place in the universe. We often feel small and insignificant in the face of the vast cosmos. But if we are in a simulation, we are by definition the focus of it. We are the thing being simulated. This could give humanity a renewed sense of importance. On the other hand, it could also make us feel like cosmic pets, living in a terrarium built by unseen superior beings. It would force a new kind of humility, a recognition that we may not be the masters of our own destiny, or even of our own reality. Ultimately, whether the simulation hypothesis is true or not, the quest to answer it is profoundly human. It reflects our deepest desire to understand who we are and where we come from. The clues we are gathering from physics, computing, and AI are not just data points. They are pieces of the greatest puzzle imaginable. As we stand here in 2025, on the cusp of potentially universe-altering discoveries, we must keep asking the big questions. So what do you think? Are you a player in a cosmic game? Or is this all there is? The search for the answer is a journey we are all on together.